Hi everyone. Today we'll be presenting our final project, which is on intersectional biases in large language models. Recently, GPT-3 has received a lot of attention due to the popularity of ChatGPT. We conducted some really simple text completion tasks on GPT-3 and noticed that there is actually some implicit gender biases. As shown on the slides here, when provided with the prompt, the doctor laughed because this model consistently gives out the pronoun he, despite knowing the fact that a doctor could be either male or female. Observing these kind of biases, we propose to create a fairness framework that will evaluate the implicit biases in this kind of large-scaled language models. Specifically, in our proposal, we will define how to identify biases in text-generating language models and establish both multi-group and intersectional fairness models. And finally, we discuss some open problems and some potential bias mitigation solutions. Specifically, we'll be using protected categories including gender, ethnicity, religion, occupation, and political affiliations. We'll also be considering their intersecting dimensions as well. We propose to generate a list of prompts based on our chosen protected groups and ask GPT-3 to complete these sentences. We will then compare the output probability distributions on both two rounds of the same prompt and two prompts that vary by some protected attributes. If the probability distribution has significant differences, we will then conclude that this language model is actually biased. Next, we'll be presenting our fairness models. So first is some notations that we use. We will be considering a set S of protected categories, and each element Si will be taking on a group of n protected attributes. When considering the intersectional fairness models, we'll be looking at some tuple of attributes representing their intersections. Specifically, we will draw combinations of specific attributes like female and Asians from the Cartesian product of corresponding protected categories, gender, and ethnicity. We will also be representing our language model with M, which takes input from X drawn from the corresponding protected attributes, and generating an output Y, which represents a set of tokens in the vocabulary that we will measure the probability of.
And next, we define our fairness models. So we first apply the notion of statistical parity on our multi-group fairness and intersectional fairness definitions. For multi-group fairness, we require that the language model output distribution to be the same for all inputs corresponding to different protected attributes on a set of properties Y that needs to be equalized on. And here note that the epsilon in the equation is a small value that sets the bound of the bias. One drawback of the multi-group fairness definition is that it treats each bias individually as mutually exclusive categories. So we solve this problem in the intersectional definition to guarantee fairness at the intersections as well. We define A as the intersection of all protected categories. And we can draw C from A, where C is the tuple of protected attributes. Then we can take two tuples Ci and Cj, and we equalize the language model output distributions for those two tuples as our intersectional fairness definition. And we also consider the notion of calibration, which is to equalize the language model output distribution with a real-world distribution R over the set of target properties Y. So for our multi-group definition, we could approximate, or we can gather the real-world distribution from statistical data. However, it may be hard for our intersectional definition because there are many intersections. So we may want to obtain R by approximating it from training data. And that leads us to the bias amplification measurement. where in the equation on the second line on the right side, you can see like epsilon would be a fairness measure of the model, whereas epsilon1 on the first line would be a fairness measure of the data set. So we can have epsilon minus epsilon1 to be how much the model amplifies the dataset bias. And for next steps, we have two open problems. So some properties Y are not suitable for applying statistical parity. For example, we do not want to equalize the output probabilities for gender-specific drugs on the attribute gender. And in that case, we may want to use calibration instead. So we want to find some way to combine calibration and statistical parity. Another open problem is how many protected categories to consider. And that is like, as the number of protected categories we have like grows, the number of intersections in intersectional model grow exponentially, which is very computationally expensive. Next. And finally, we define some bias mitigation strategies. Before training, we can use data augmentation to reduce the biases in the data set. Whereas during training, we can use our fairness model and metric as a differentiable regularizer that can be added to our loss function for training a model that's fair on that metric. And finally, for post-processing, we can apply the multi-calibration algorithm to adjust the model output distribution to the real-world distributions. And that's it. Yeah, thank you for watching.